Hello students, in this session we are going to study combined bending and torsion. On a shaft, if there is bending stresses as well as shear stresses due to torque, so what is going to happen? What are the shear stresses or normal stresses developed in this material, and where are the chances of the failure, right? Suppose talk about the bending stresses, right? You have already read about the bending stresses, or if you have not read about this, go to the chapter of bending stresses and read the stresses in about the bending stresses, right? So let us talk about bending stresses first. So what will happen? Suppose we have a beam like this, suppose we have a beam, suppose we have a cantilever beam, and we are applying a load here, W. What is going to happen with this beam? It will elongate like this, you will see that there is increase in length of this fiber AB. AB length will increase like this. This will become here, suppose B dash, and this CD will compress, right? There will be compressive stresses. Basically these are the bending stresses, right? This D dash. So you will find that AB, when we are applying, so AB, the elongation is there, increase in length is there of AB is less than AB dash. So there is increase in length of AB, increase in length of AB. So there is elongation, it means there is tensile stress developed in the material, and that tensile stress is the bending stresses, right? So bending tensile stresses, so bending tensile stress developed, tensile stress in AB. So in AB there are bending tensile stresses are there. So you will see here that if I show a point, so there will be some tensile stresses developed in this material like this, right? So I have made here a stress element like this, on AB. So there are tensile stresses, right? Sigma B. Bending, because these are bending stresses, so bending tensile stresses are there, and these are maximum at the outer fiber. This is neutral axis, at neutral axis there is no stress. This is neutral axis, at neutral axis there is no stress, but at the outer fiber the bending stresses are maximum. So at outer fiber the bending tensile stress is maximum. This you can go to your bending stress chapter and read that, right? So what is happening with when we are giving a we are applying a load and there are bending stresses are developed in the material, right? What is going to happen in that case? So there is increase in length of AB and there are bending tensile stresses are there, and at outer fiber the maximum bending stress will be there. This is sigma B max basically in this material, right? And here in CD, this is a compressing taking place. You can see that the compressive stresses are there. This is a hogging bending moment, basically hogging bending moment, right? So you will get this type of bending moment is there. This is hogging bending moment, right? Like this, right? So this is a hogging bending moment, right? So outer fiber will be in tension and lower fiber will be in compression. So there will be compressive stress developed in this material. This is sigma B tensile, this is sigma B compressive, right? Sigma B compressive, and there will be shorten in length shorten in length of this CD, right? So CD is greater than CD dash in this case, right? CD is greater than CD dash, and there is decrease in length of CD, right? And bending compressive stress developed in CD. So bending compressive stress developed in CD, right? And these stresses are zero at the neutral axis and increases when we go from center to the outer fiber. So at CD dash or CD, the stress will be maximum. So at outer fiber is our CD, right? Here the outer fiber was AB, outer periphery, right? So outer fiber CD, the bending compressive stresses are maximum, zero at the neutral axis, and as we go from center to the outer radius, these are the maximum. So these are the basically maximum stresses. These are basically the maximum stresses, maximum compressive stresses. Similarly, these are also the maximum tensile stresses. By the maximum bending tensile stresses this, and maximum bending compressive stresses this. So at outer fiber we are getting the maximum stresses, right? So there is a chances of failure at the outer fiber due to bending, right? Outer fiber the stresses are maximum, so chances of failure are there. But here we want to study the combined bending and torsion, that we are applying a torque also, and if we are applying a torque, the shear stress is also developed due to that torque. And what is going to happen? And there will be two types of stresses. Then at a particle there are two stresses, bending stresses and shear stresses due to torque. So what is going to happen? Let us study that. Now what is happening here is we are applying both bending and shear stresses, right? So suppose this is our beam or shaft at which a load W is applied, cantilever beam is there, and also a torque is applied, right? So due to torque there are shear stresses developed. This is our neutral axis, this is the neutral axis, and this is AB, and this is CD. So due to torque there will be shear stresses developed, and it is maximum at the outer periphery, you know that. And due to that W load there is in the cantilever beam there is bending stresses developed, which is maximum at the outer periphery again, right? So that you can see the diagram for that. You can see here there are two types of stresses developed. There are two types of stresses will be developed. These are the bending stresses like this. Go to bending stress chapter. This is tensile, and this is compressive, right? So this is sigma B compressive, and this is sigma B tensile, right? And this is maximum at the outer periphery. This is maximum at the outer periphery. So this is a linear variation of bending stresses. And again also there are shear stresses. Similar way, this is maximum at the outer periphery. These are the shear stresses developed, right? Like this, right? And this is again shear stresses are maximum at the outer periphery. and these are the bending stresses, and these are the shear stresses, right? So these are the bending moments. These are due to bending moments. Due to this W load, there will be a bending moment developed, and due to that there will be bending stresses, and these are due to the torque applied T, right? So there are two types of stresses, and both are maximum at the outer periphery. So there are chances of failure at the outer periphery. So if we took a point, say P, and we see what is happening on this P, we will see a stress element P like this, this P I am making here, at which there are bending stresses which are tensile, and there are shear stresses due to torque. There are shear stresses. You can see here this torque, the shear stresses are there like this, and shear stresses are only complementary, so there will be a complementary shear stress also. So this type of stress condition is there. Where sigma B is the tensile stress, bending tensile stress, which is maximum at the periphery. Though this is maximum, sigma B is maximum, and shear stress is maximum because it is at the outer periphery, and the dia of this shaft is, say, D. We want to find out the further maximum stresses in this case, because this is a stress element, and you know that principal stresses are the maximum stresses, or we can also find out the plane of maximum shear stress, the amount of maximum shear stress or amount of maximum normal stresses, which is principal stresses. So what are the principal stresses in this case? Because failure will take place due to that principal stress if the material is weak in normal stresses, or the failure will take place the maximum shear stress which will be developed at a certain plane, because if the material is weak in shear, right? So our aim is to find out the principal stresses and maximum shear stresses, right? So our aim here is to find out maximum normal stresses or principal stresses, because these are the maximum stresses, and if the material is weak in normal stresses, then the failure will be take place here, and the maximum shear stress, because if the material is weak in shear, then the failure will take place due to these stresses. So this is our aim, is to find out at the outer periphery, and outer periphery stress condition is this. Now you go to chapter number 3, where we have used the formula for sigma 1 and sigma 2 principal stresses and sigma T max shear stresses. Remember that formula and try to find out the maximum stresses. What was that formula? Right? So I am writing here the formula. What is that formula? Sigma 1, sigma 2 principal stresses. Sigma 1, sigma 2. What are the principal stresses, right? What was that? That is sigma x plus sigma y by 2 plus minus under the root sigma x minus sigma y by 2 whole square plus tau square. So this was the principal stresses. And what was the maximum shear stress? Sigma T max, that was this term only, under the root plus minus sigma x minus sigma y by 2 whole square plus tau square. So this formula you will obtain from the chapter number 3, the chapter of principal stresses, right? We have to apply this formula to obtain the principal stresses and maximum shear stresses, because failure may take place at these stresses, right? And stress condition is this. So sigma x is sigma b. In this case, sigma x is now sigma b. Sigma y, there is no sigma y in this transverse plane, there is no stress, so sigma y is 0. And tau tau, this tau is tau, right? And it is negative because when deriving these formulas, shear stress was taken in the opposite sense, right? So here tau is basically minus tau here. So this is the stresses. Sigma x is sigma b, this is sigma b, right? Sigma y is 0, there is no stress in y direction, and tau is minus tau, this tau, which is in opposite sense of the our sign convention, or we have taken the reference stress element, right? So if I put here the value of sigma b and tau, what we will get? The value of sigma b and tau, what we will get, right? So put the value of sigma b and tau. So sigma 1 or sigma max, I am writing directly here sigma max, and I will take the positive sense only. So sigma max will be equal to, sigma x is sigma b, so sigma b by 2. Now I am omitting the minus sign, plus under the root sigma b square by 2 square plus tau square. So sigma b square by 4 plus tau square, because minus will become plus. So sigma max will be equal to, you can take 1 by 2 out, and you will get sigma b plus under the root sigma b square plus 4 tau square. This is our sigma max. Sigma max half sigma b plus sigma c b square plus 4 tau square. This is the formula. This is equation number 1. But we know the torque applied and the bending moment due to this W, right? So we have to convert this into torque and bending moment. First we want to find out sigma T max. What is sigma T max? This is the sigma normal stress max, now shear stress maximum, sigma T max. That will be equal to sigma b square by 4 under the root sigma b square by 4 plus tau square. When you solve it, you will get the formula sigma T max as half under the root sigma b square plus 4 tau square. So this is our maximum shear stress, and this is equation number 2. This was equation number 1. This is equation number 2. So we have obtained two equations, sigma normal stress maximum half sigma b plus sigma b square plus 4 tau square, this equation, and sigma T max half sigma b square plus 4 tau square under the root, right? These two equations need to be further solved in terms of torque and bending moment, because using the bending moment diagram, we know the bending moment at the outer periphery. What is bending moment at the outer periphery? And what is the torque applied? T. So we have applied the torque, we know the bending moment due to applied torque W, and use this here and find out the final result in terms of torque and bending moment. So we have obtained these relations, sigma max this value and sigma T max this value, right? Using that sign our stress element at this point P, we have obtained this value. But we want to find out further solution of this, that in terms of torque and bending moment. So what is the value of sigma b and tau in terms of torque and bending moment? Go to our bending equation. What is our bending equation? Go to the bending equation. What is that bending equation? Remember the bending equation, that m by I sigma y E by R. Go to the chapter of bending stresses and you will get this bending equation, right? In this equation, we have to find out sigma b in terms of m. Sigma b in terms of m. So sigma b will be equal to my by I. My by I. And what is y? What is y? Y is the outer periphery, the distance in vertical direction, and that is the outer periphery, that is d by 2. So y is d by 2. And what is I? Moment of inertia. If it is circular, suppose this is circular. Suppose this is a circular cross section of diameter d, then the moment of inertia of a circle is pi by 64 d to the power 4. So you will get sigma b as, so finally you will get sigma b will be equal to, solve it and you will get sigma b as 32 m upon pi d cube. 32 m by pi d cube. This is the bending stresses at the outer periphery in terms of bending moment. So shear stress is in terms of torque. Go to torsion equation. Go to torsion equation. What is that torsion equation? T by J tau by R G theta upon L. This is our torsion equation. And from here we can find out shear stress in terms of torque. So tau will be equal to TR by G, and that will be equal to T R radius. Radius is the outer radius because we are talking about the outer radius, that is the d by 2, and J is pi by 32 d to the power 4 polar moment of inertia. So from here you will get the shear stress at the outer periphery at as 16T by pi d cube. 16T by pi d cube. We have obtained the shear stress at the outer fiber at bending stress at the outer fiber sigma b and tau. Using this, put these values in this formula, you will get the maximum normal stresses, which is principal stress, and maximum shear stress at which the failure take place, right? So put these values in this equation. So you will get sigma max as half sigma b. Sigma b is this 32 m by pi d cube. So 32 m by pi d cube plus under the root 32 m by pi d cube square plus 4 times tau square. What is tau? 16T by pi d cube. 16T by pi d cube square. So this is the sigma max, right? Final result can be obtained by taking some values outside, and you will get the final result as sigma max will be equal to sigma max. What will be the value? 16 by pi d cube under the root bracket m plus under the root m square plus t square. So this is the maximum stress which you have to remember. The value of maximum stress 16 by pi d cube m plus m square plus t square, right? So this you have to remember. This is important. So this is the final result of maximum normal stress when there is combined bending and torsion. Maximum normal stress or principal stress where there can be the failure. So this is 16 by pi d cube m plus m square plus t square, right? So remember this and you have got your result. Now what is maximum shear stress then? Maximum shear stress. Maximum shear stress. Tau max, sigma t max, sigma t max. Now we want to find out sigma t max. So sigma t max will be equal to half under the root sigma b square. Sigma b is 32 m by pi d cube. 32 m by pi d cube square plus 4 times tau square. Tau is 16T by pi d cube. 16T by pi d cube square. So this is a sigma t max. Solve it and you will get the final result as 16 by pi d cube. So sigma t max will be equal to 16 by pi d cube under the root m square plus t square, m square plus t square. So this is the maximum shear stress due to combined bending and torsion. So these two results are very important. Whenever we will design our shaft in machine design, when you do it and you have to find out the maximum stresses in a shaft due to bending and torsion, you have to use this result for the design purpose, where the maximum normal stress will be this. Failure can take place at this stresses if the material is weak in normal stresses, and the failure may take place at these shear stresses. These are the maximum shear stresses if the material is weak in shear. So these are the two most important results which you have to keep at your tips. So this was the topic of combined bending and torsion.